Okay, we're back with the last example from class 16, and I think I have an extra credit that's going to be assigned or available where you can work through a problem not too dissimilar from what we're going to do here. All right, so here in this example, we want to determine the mean torque of a single-cylinder four-stroke engine that produces a torque that follows a curve that's approximated like this right here. We'll take a look and see what that actually looks like, where theta is in radians and the nominal speed is 2,400 RPM. When I determine that mean torque, estimate the greatest energy fluctuation occurs. Estimate the greatest energy fluctuation occurs between 0 and 180 degrees using a coefficient of speed fluctuation of 0.1. Find a suitable value for the flywheel inertia. And then we want to find what omega 1 and omega 2 is. And I think by that, we mean we want to find the maximum and the minimum. But let me double check by what I mean. Yes, okay. So what we're going to do is we're going to take a look at the this curve right here. All right, so it looks like this. If we were to plot this out, and this is in Excel, plotting as a function of theta, we will see. And so this right here tells us what we were talking about before, that the greatest, this right here, we're going to say that this guy is going to drive the thing along. Yeah, okay, so this is like the driver right here of the whole thing, even though this does have positive. This has, there's negative energy right here. So what we want to do is find that total area underneath there, and we could do that by integrating this equation right here. So let's see what I did. I found from 0 to 720 degrees right there is, I gotta be careful about the units. Okay, I see how I did, because I went over here and I went to theta pi and I went to theta divided by pi. I want to be careful. I'm a little concerned that the units are going to be working, because I said from here to degrees. See, let me see what happens. Okay, so this is a good usage of our online tools right here. Let's see. Do I have Wolfram Alpha as a bookmark? I do not, so I need to open up my, this doesn't like doing this when I'm, come on, there you go. So I go Wolfram Alpha, and obviously I use it because it was the first guy up here, and I can go into the note sheet right here, and let's see, copy that out and come back into Wolfram Alpha and paste that into there, and let's see what happens. All right, so you can see they have the thing graphed out for us, and they've taken and they've done these things by degrees. My concern here is that it doesn't know the difference between degrees and radians. That maybe that I messed that up. Right here I have 3,919 as the answer, is the area underneath that curve. I might want to double check that. Now what I can do is, hopefully I have this somewhere where I've done it. Let me double check where this came from here. I have torque data. I have the solution, homework 7. Let's see. This isn't up to date, by the way, so Doesn't matter. So you can see what my little graph things look like. Why do I have this thing right here? All right, so disc brakes. There's problems and problems. You could do now. You get to see that over the years I have done many different problems and final exams and blah 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 blah. Homework. Okay, this is all right. Okay, this is a different example. This is the example out of the book right here. Class 16 example. Here you go. So what I did is I plotted this out. Okay, so I took let's double check this right here. I took this thing and I'll go back to this. Will it let me do that? Yeah. And put it into here. Let's say paste. I just want to paste. All right, there you go. So yeah. Okay, sure. I need to escape out of that. So what you're seeing right here is going to be the sine of that theta right here. So it's that guy right there, and a turning this radians. I just want to double check my thing here. Yeah. Say, I think I get the same answer from this. Let me double check. I took the sum of this here, right here. Here's the sum of all of those things right here. The sum of the integration of this. Yeah. And so, but you can see I get the same answer right here as that right there. But I'm just questioning my, I guess I got to escape somehow. I have to hit escape, but I don't have my keyboard attached right now, so I'm not sure how I do that. Without, All right, so let me see. Can I just hit escape? Oh, it's going to flip everything upside down, and I've managed to mess everything up. So this is a great video. All right, there you go. Hit undo. And I took the sine of this angle right here, which is supposed to be this should not be omega there. That should be theta. That's what's really messing me up. Is that shouldn't be omega. That should be theta. All right. So and I took and I multiplied this by it's 1 up here. It's the pi now that's interesting me, and then I'm taking it e to the minus thing. Let me see. Oh, okay. I see what I did there. Okay. So yeah, that's what works out, right? So I took sine of this, and 1 was just in case I wanted to put a coefficient in there. So that's what that was, all right? So I am taking the sine of that angle right there, and then I took e raised to the negative of that angle divided by 180. Okay, so that's the same thing as taking it and dividing it by pi. So I just skipped that step. And then I took this magnitude, this coefficient right here, and so that's what I got. This is going to be torque, and then that's what that got plotted right there. All right, so that is that thing plotted there. That's fine. And then here I'm going to integrate and take for my increments right there. There's incremental delta theta, which is up here, and that's times pi right here. And so and then once again I'm screwing this whole thing up right here. So I'll go, I gotta hit enter or something somehow. Let me hit enter and then be done with it, and then go undo. There you go. All right, so I'll go undo. Boom. And then what I did is I found, and by the way, you could follow example 16 something 16.6, I think, in the book, kind of goes through this process. And I think they either just tell you that they integrated it or they do it in a table. But anyway, I'm doing it numerically integrating essentially here by using an increment of 15 degrees is what I've done. And then and then you'll see this next step right there. But anyway, I do get the 3,894, which matches me getting it from right here, 3,919. You'll know there'll be a difference because I was numerically integrating the thing. There's my concern. I think it does recognize what the units are. It's this pi that was bothering me right here. Whether that was going to be correct right there, but I think it does work out correctly. Now back to our regularly scheduled program. I just was concerned there. So what I end up getting here was equal to 3,919.4, and I believe that torque was measured in inch pounds or foot pounds. It's probably foot pounds. Let's see, what did I write down? No, they were in inch pounds. And then we also want to go from the 0 to 180. These are degrees. So let's go back and keep this. And that's one of the nice things about this Wolfram Alpha is we could just go up to here and go 180. Where's enter? Enter now here? Okay, I guess we'll go back to here. Hit enter and close that out. And Wolfram Alpha says that it's 5,461, right? So that's the this is the energy that's driving the thing is 5,461.2 inch pounds, right? And so this is going to be like the E of the power of the thing, and here's the E total. Now, so we're going to get what the mean torque is going to be that 3,919.4 divided by our delta theta, which is 4 pi, right? And that ends up being 311.9 inch pounds. And this is going to be true. That's going to end up, if we had this right here for the average speed that's taking place, we'd find out that that's like 11.9 horsepower. I think I might calculate that somewhere over to the side. Okay, yeah, if I were to look at that 2,400 RPM, multiply that by that mean torque, that's what we could expect as being the output. Now, I want to reintegrate a curve that goes from 0 to 180 right here. And I'll take this integral up here. Well, this guy right here, but I'm going to subtract out the t mean of the thing, right? And so that's going to be d theta coming up here, and I get 4,481.4. And that's going to be equal to, and then we want to, that's going to be, we integrate right there. That's going to be, we call that delta E max, right? So that's the difference between the max and the average right there. We subtract out that 311.9 out of this thing right here. Is that true? Boy, that seems like it's not true. But yeah, I think so. Yeah. So like I think if we were to take this and come back in here, let's say we're going to keep this, and hopefully, let's say we come right up into here and we go minus, that's not minus, that is an underscore, minus 311.9. And boy, my face will be covered in egg if this doesn't come out the right thing. And we're taking it from 0 to 180. I'm not 100% sure I believe that 0 to 180 thing. But let's say, what do we get as a value here? Yeah, 4,481 is what that's going to turn out to be. And so when we want to find the moment of inertia for the thing, whoops, I accidentally used that. I'm going to go into a slideshow. I is equal to delta E divided by CS omega squared. And by the way, something that I don't think I ever showed it up in here was that omega is going to be 2,400 divided by 60 times 2 pi, or 251.3 radians per second. So when we get down here, we get the 4481.4 and divided by 0.1. Do I ever say anywhere in there? Yes, I do. That's one of the givens. So we might want to have gone through, by the way, up through this thing and said, well, what kind of what was our goal right there? Was something moderate variation maybe was our goal. Like 0.1 would have been in that. So that was our thought process when the problem was written and we were provided it, right? There was that 0.1 was going to give us that kind of a variation. So 251.3 squared, and we get a 0.7094. And we got to be careful what these are going to be. These are, according to looking through here, we have inch-pounds force, right? And we have omega squared. So we are going to have pound force and pound force square, and then inches, right? If we were to take a look at the conversion that we would need here, I think we want to generally have for the units for a moment of inertia, at least the ones that I want, I usually want a slug foot squared, right? Because it's going to be mass times a distance squared is what mass moment of inertia is almost always going to be. So I would make the conversion here, and I have to double check what this is. Maybe I could do that live because no one's going to watch this video anymore anyway, so it's not that a matter that it's that long. That you would have 0.7094. 0.7094. We're almost certainly going to multiply that by, divide that by 12, right? Because we have an inches here. So we want to get that into feet before we do anything else. So we divide by 12. See, yeah. And then, and I believe that once we have a pound for, anytime that you're looking at, let's see, I'll write this over to the side right here. Just remember, when you're dealing with the units, you don't have to divide by 32.2 unless something was already in terms of weight. Just remember that a pound force is equivalent to a slug foot per second squared, right? That conversion holds true. The only time you divide by 32.2 is if something was already provided as a weight, and then you wanted to turn it into slugs. But if it's a units conversion, it just equals force is equal to mass times acceleration, and a slug is defined by that foot, right? That foot per second squared. So when you see this combination right there, you could always substitute a pound force into a slug foot per second squared. And so all we needed to do was to turn this into pound force second squared feet right here. And then we were able to substitute this slug foot per second squared, and so then we were going to, and so all we had to do was multiply by 12 to get it into that, and then all of a sudden the units turn into there. So these are the slug feet squared. I hope you follow that, right? This is an important thing. I've messed this up throughout my career, so don't you be like me. Try to rationalize and or work the thing out methodically. And I've gotten to the point where I'm better at it, but I certainly do fall into that pitfall where I can get confused by the units. And then the CS was defined by the max minus the min, and I write them as 2 and 1, about the mean right here. So the fluctuation that you can expect with that CS is going to be, well, we could have 2, the omega 2 is going to be the CS times the omega mean plus the omega 1. But we can also make the assumption that omega 1 is equal to 2 times omega average minus omega 2. It's sort of a rough edge. It's sort of because you don't know that it's going to fluctuate between just two things. I mean, it could be all over the place, right? Boom, boom, and by the way, that's not fair because we shouldn't make that. We could make here's the zero, and here's the minimum right here, and here's the maximum, and the average could be right up in here. And you don't know that the average is going to be the minimum and the maximum here because it isn't necessarily always going up and down between those, right? It isn't spending as much time at the max as it is the min. But you could make this sort of general thing. So you have these two equations and two unknowns, and what we're able to do is substitute one for the other. And based on this, and by the way, we don't even have to turn these into radians right here. We could just take the 2,400 right here and put that in there for the mean. And what we would be able to find, I guess maybe I did the algebra out, and I got 1/2 omega average CS plus 2 is what I worked out for by working through those two things. And I was able to find that my maximum, or my 2 here, I would say, if it's just fluctuating between two values, was 2520 RPM, and then my 1 was 2,280 RPM. So hopefully that makes a little bit of sense. And I probably botched it all up by trying to cram some stuff into this right here. But hopefully you can take those equations and you can trust what they are. So let me see how far I am right now, because I want to extend this video to the second example. I'll keep all this stuff, and I just want to double check and see. 23 minutes into it. That's a really long video. I guess I'll continue anyway here. So here is an example where we take a small engine's flywheel, and I do believe that the see, come on, hide it. Why is this thing not hiding? Okay, I want to minimize them. There you go. I can do it. So I took this other example and I came up with this. This is my own example, as was that one, but that was sort of a modification. And okay, so I think I actually took the flywheel weight from something, and I have right up here. Whoops, sorry about that. Let's see. I'll go back to it. Make a pen. I'll go purple. And I have this as 6.673 pounds. So I have a small engine flywheel, and its kinetic energy at That's not a question or a statement, and it's kinetic. Okay. The flywheel weighs 6.673 pounds, and its dimensions are, and I believe I measured this myself off of our small engine, 6.7 inches outside diameter, 1/2 inch outer rim thickness, 1.6 inch outer rim width, and 0.3 inch inner hub thickness. Okay, well, I'll draw what that means. The weight density of the steel is 0.284 pounds per cubic inch. I say find the mass momentaires for use in the homework. I don't assign this homework problem, or maybe it's the extra credit one. But anyway, what we have in terms of this flywheel is something that looks like this right here, right? So here's the dash line, and it doesn't go all the way through, right? So it looks from the side to be like this right here. And I didn't account for the fact that there's a hole right here, right, that the shaft passes through. But I say that this right here is 0.3. This right here is 1.6. This thing has a diameter of 6.75. And this thing has a thickness of 0.5. And if I do this, I could find what the volume is going to be. Is going to be pi over 4. Okay, so yeah. So what I took the pi over 4 was going to be double checking here. Oh, I see what I did. I did it as if it was a cylinder minus a cylinder. Okay, so I know that, but the area of this whole thing is going to be 6.75 squared times pi over 4, and then the volume is going to be that times 1.6, right? And then I also know instead the inner part, I could subtract out the inner part, which is going to have an area right here, which will be 1, because I'm going to subtract out 0.5 and 0.5. Is that true? I'm not liking the answer. I'm not liking what I think. Oh, no, I see. Okay, it's going to yeah. So that's 5.75 squared, right? Is going to be the diameter of this piece of this inner face right here, and then the depth is going to be 1.6 minus 0.3. So we get 6. Come on, I decided not to do it. 6.75. Squared. Why is this not working? All right, it doesn't like it when I rest my palm on the screen sometimes. That's not why this thing works, by the way. I thought for a while that's why it does it, but I can balance my hand on over to the side, and it doesn't do that. So don't try to claim your $100 that I offered based on that. And then 1.3. And that's all there. Okay, so what I end up for the volume is 23.50 inches third. And yeah, so this is the weight of the thing, was the specific weight times the volume. So I did all that, but I actually, in the problem and up above, I just gave the thing, right? So that right there, this is the density of steel. Density of cast iron is probably not too much different from there. I also one thing I should have done right here was figured out, this is sort of a waste, because the way that I would go about and find the mass moment of inertia of this thing is I would say the velocity of so I did it a totally different way. This is all messed up. I should restart the video, but I already recorded the other part, so you can just fast forward through all this. You probably already did. You probably didn't even start watching it. We could take a disc, which is going to be this part right here, and we could take a ring. That's going to be the easiest way to... there you go, my ring right here. And so for the disc, you get the volume of the disc is going to be pi over 4, 6.75 squared times 0.3, and you get 10.74 cubic inches. And then so the mass, or I should say the weight, if you will, of the thing is the weight. Actually, I hate that. So the weight of the disc is going to be 3.049 pounds, and then of the ring itself is going to be pi over 4, and then 6.75 squared minus and something so 5.75 squared times 1.3. And so why is it 1.3? Because we want only this part right here. We don't want to go all the way to the front end, so it's not times 1.6, and that ends up being 3.625 pounds. And I sure hope that they add up to the other thing. That's the weight of the ring. So if we were going to get, do I ever divide by 32.2? I should have divided by, all of these are in inches right here, so I should have divided by 144. I guess I wait to the end. So I get the I of the disc is going to be mass, or I should say weight in this case, weight d squared over 8. Right, so that was 3.049, 6.75 squared over 8. I end up getting 17.36, and this is going to be units of pounds, force, inches squared. And then for the disc, or for the ring, I have something similar, but instead it's going to be weight over 8 times the dO squared minus di squared. And if we stick those things in there, we end up finding that it's 35.62 pound inch squared. And so the I total is going to be 52.99 pound inch squared, but we want to divide by 32.2 and multiply by 144 square inches per. Actually, we want to divide by both of those. And what we end up getting is I of the total in the units we can use, 0.01143 slug feet squared, right there. All right, so this is sort of a review of something that you might want to have done. I think I included it in there in a previous year, and that was in my notes, so that we would have, so that students wouldn't have to go back to the very basics to try to get the mass moment of inertia, but also to have some of the discussion about doing that. So that was the video right there. It was way too long. I'm not sure that this part was necessary, but I'll take a look and see what I assigned and see if it was or not. So I guess I have to delete a lot of that stuff. So let's see how long that was. It was 33 minutes, but once again, this was just sort of supplementary information, and maybe it'll be useful to you if you decide to do the extra credit, or maybe you would even keep some of the links to some of these videos for later use. But I'm going to use these again probably. So I don't have a video going on here, so maybe I should figure out a way to do that, right? So that I could record a video. But if I don't have it like as part of this thing when I set it up, right? When I start this up, I can't transition into it. So what if there's a way to just click onto here and write some video? I'm experimenting, so it'll make the thing longer. But let's say I just go camera. Let camera access your precise location? Sure, why not? Okay. So what I can do is, I think, actually it's going to be mad at me. See, what guitar do I have? I have my Jimi Hendrix-esque Strat, made from, once again, these are a parts guitar made from Warmoth parts, but this is, and it's not really a Fender. It's a I bought the logo, but it's a reverse Fender, but it probably looks correct on this camera. Is that true? So look, yeah, it should be a mirror image. In real life, that's a mirror image. Because this guitar is supposed to look like it's upside down, even though the knobs are in the correct spot for replacement. So that's what makes it like a Jimi Hendrix type guitar, because he was left-handed. And I think they made left-handed guitars back then, but they were rare. But he preferred the right-handed guitar. I guess he'd always been playing it that way. He couldn't afford maybe the left-handed one back, because they used to actually be more expensive. So he got a hold of right-handed Fenders, and he just flipped the strings, and he played them upside down. So it was kind of weird looking right here, him playing. Sometimes the guitar looked like it was backwards, but it was actually, the strings were correct. But one of the bad things is that, like, now your hand doesn't have access to as much to these strings as it would from this side. Also, this tremolo was on the wrong side, right? So it was actually underneath his hand, and so were all the knobs. I've played guitars that, they actually made one in 1996 that was like this, and I wanted to buy it because I'm a huge Hendrix fan, but it was just too annoying. But then, so like I saw when Warmoth started making this reverse body, I thought it was really cool. And then Jimi Hendrix set his guitar on fire, probably a couple of them, but very famously at Monterey Pop Festival. He set it on the ground and poured lighter fluid on it and was pretending like he was lifting up the flames. There are famous pictures and video of him doing that right there. It's almost in tune. And it's a little weird tuning the lowest string with this guy right here. Now, there's people who insist that this is there's a different sound produced because of because the string lengths above the nut are different. Now, I'll concede that when you're bending a string, definitely the difference of the length of the string above the nut can feel a little different, especially when you're making really big bends, because there's more string to stretch. So it kind of makes sense that there isn't necessarily as stiff when you're making a large bend that would stretch the length of the string. Now we're able to, in terms of the strain energy that could be placed into the string, would definitely, because there's more string there, it's longer string. But I don't think the sound changes any. And one of the things the arguments I would make as part of that is that when you have a locking tuners, right, or you have a locking nut, I should say, up here, which many guitars have. I'll show a guitar or a couple of guitars I have that have locking a nut, that doesn't really affect the bending, and it doesn't affect the tone. Everything up above now is like, you could actually just once you lock the nut there, you could just unwind these strings. So nothing up here really matters. So I don't know if it really makes that big of a difference. But there's people who are going to insist on that kind of thing, and nothing you could do that can change their mind. And so I think I might have some. It doesn't sound quite right. I think maybe something's screwed up here. Oh, I still have the tuner on. That's why. Boy, that really. I think I need to adjust something in there. I think it's the getting the hum from something. Maybe it's the computer monitor. I don't know. That's a lot of hum. I don't know. Let's put in a British classic sound. forgot how to play this. I'm pressing too hard on the frets. Or it already went out of tune? Yeah, there you go. It's already out of tune. So anyway, video went too long. I won't even mention how long this was when I'm done with it. But ta-da!